So my name is Pavithra. I work with the TensorFlow team with Francois, focusing especially on Keras. And I joined this team about 8 months back as a machine learning newbie. And I got the opportunity to work on writing a text classification guide. And it was a great learning opportunity. So that's what I started with in the team. And this talk is going to be about the guide and about Keras as well. So what I want to go over in the next 20-25 minutes is the following. So starting with like what we set out to do, and for that, like we conducted a number of experiments. So I'll go in detail about it in some time. And the results that we got, there were some surprising ones for us, and about Keras, the framework, and conclusion. So there are a lot of guides, tutorials, and examples available out there. So what's special about this? So let's say you have a machine learning problem in hand. I heard some of your introductions. I'm assuming a lot of you are focusing on ML problems. So we all naturally look for examples, tutorials online. And what we find is many of this is targeted towards a specific use case, like it's either focusing on a single model or it's focusing on teaching you just text classification. It may not work for the problem that you have in hand. So what we wanted to do was create end-to-end workflow that would work for different use cases. It would provide you with a guide for choosing a model, and along with that, provide best practices and code snippets that you can easily copy for your use case. So the first problem that we wanted to look into was text classification. This was an obvious choice, like because of the number of applications text classification has. And I'm sure like within the last hour, like most of you would have used text classification ML applications, starting with simple email filtering. And there are a lot of misconceptions out there that only like RNN models work best for text classification. This isn't always the case, and we wanted to test that as well. So our goal was to provide, like as I mentioned earlier, end-to-end pipeline for text classification that would include sort of guide for choosing a model. And with that, we'll provide code with TensorFlow using Keras high-level APIs. So for that, like to be able to develop this guide and figure out like what model to use, we had to run a number of experiments. So the idea was that like with the experimentation, we would be able to sort of find a pattern in the data. And with that, we'd be able to develop a flowchart and pipeline to help with classification. And this meant that we'd have to try out a lot of data sets and many different types of models. And for depending on what type of model we choose, we have to do different types of data pre-processing and choose different sets of parameters. And because of that, we ended up training around like 400,000 models. And this meant like we had to decide where to train all of these models. So naturally, our first choice was Google Cloud Platform. And we wanted to train like all of these models in parallel, and we chose to measure accuracy and time as a metric, and we wanted consistent metric information from different instances that we are running the experimentation on. So that's the reason we picked GCP, and I ran the experiments on like 126 instances. This was just a random number I picked based on the number of data sets I had. And I went with a simple configuration, single GPU, run one experiment at a time in one instance. So now we have the machines, and then we picked which data sets to run the experimentation on. And we started with like 8 data sets, which includes like classic text classification data sets like IMDb, Rotten Tomatoes, Reuters, 20 News Group, and so on, and also some different ones like Tweet Topic, which is a weather classification data set. So we ran all of our experiments on all of these data sets, and once we saw patterns emerge, we added more data sets and ran additional experiments on them. So we have the platform ready and the data sets. The next thing is to choose the models. So basically what we did was divide the models into two categories. One is models which can leverage the sequence information, that is ordering of information in text, which is models such as CNNs, RNNs, and these we categorize as sequence models. And anything else which doesn't necessarily leverage that ordering information, we call it n-gram models, because for these models, we pre-process the text as n-grams. And what I have here is all the different parameters that we use for pre-processing. So I'll just quickly go over them, like all the details. I'll share the link to the guide and the code at the end of this talk, and all the details are available there. And so basically what this means is when you take a text, whether you split the text into words or characters, that is one parameter choice that you have to make. Commonly used option is word. And the other parameters are like if you're pre-processing your text, splitting into n-gram tokens, whether you split it into unigram, bigram, or trigram. And count mode here indicates like how you represent the tokens in numerical form, whether you just use binary or you use count mode where you it basically indicates the number of times a token appears in a text, or you use TF-IDF, which is term frequency, inverse document frequency. So basically, all of these are the various parameter choices that we experimented with. And so because of these number of different options, we had that many experiments run from. And what we saw was that like at the end, we were able to develop this kind of flow chart. I know it's not very clear. I'll zoom into it in a bit. So basically, you can see there are two main branches, one for n-gram models and other for sequence models. And every box here indicates like a parameter and what choices we tried and what worked best. So just zooming into the first part. So as I mentioned earlier, like the commonly followed practice is to split text into words, and we found that was true as well, like with experiments, like splitting into characters didn't work really well. And second, like how do you choose whether you have to go with n-gram or a sequence model? So for this, we found that the amount of data that you have plays a key role in this. So the number of samples that you have and the number of words per sample helps decide whether you go with a simple n-gram model or a sequence model. So when that value is very small, we found that a simple n-gram model is sufficient. Otherwise, sequence model works best, such as CNNs, RNNs. And so the n-gram among n-gram ranges, like found that you don't have to go for higher n-gram ranges. Sticking with smaller, like unigram, bigram works well. So among the other parameter choices, like when you split text into n-gram tokens, you can use TF-IDF function to convert that token into numerical value. And there wasn't much difference using just a simple binary representation as well. It was just marginally better. And once you have converted your text tokens into numbers, the next thing that you do is find the correlation between each of those features with the text classes. And you can do that with different scoring functions. And the functions that we tried were fclassif and chi-square. And we found fclassif to be better. And now we have the scores for each of these tokens. The next thing to do is to rank them. And we found that like choosing at most like 20,000 features is sufficient for any problem. Anything more than that does not add any value. And sometimes it may even lead to noise. That is, it can cause overfitting and reduce the performance. And in both the n-gram and the sequence case, we saw that normalization did not really influence the result, at least with the metrics that we tried that much. And is shown here. Like for n-gram models, the model of choice was simple, like fully MLP here stands for multi-layer perceptron, a simple fully connected model. In many cases, a 2-layer MLP worked great, and this is the route that we chose for classifying IMDb dataset. And when it comes to sequence models, like typically we have embedding as a first layer in sequence models, and so we found like the same number of samples to number of words per sample ratio to help here as well, in the sense that when you have really large number of data, you can learn embeddings from scratch from your data set, and if not, it's best to use pre-trained embedding weights, such as the popular ones are glove, word2vec, and so on. For our experimentation, we use glove embeddings, and we fine-tuned our model with glove embeddings, and for the cases where the ratio of number of samples to words per sample fell in between like the smaller n-gram range and really large data set. And as far as the sequence model goes, I found separable CNN model, 4-layer separable CNN model worked best, followed by CNN model. So basically what this provides is, with this flowchart, like you can, for your problem, knowing just few characteristics of your data set, you can make choices for various parameters very easily, and then have a model which will give close to best case accuracy results. And then you can play around with it and tune it and try like if you want for your use case, try fancier models like RNN with attention, things like that. So quick recap about the flowchart. Basically, the number of samples to number of words per sample ratio, we found like plays a very key factor in how you choose a model for text classification. And when that is very small, a simple n-gram model is sufficient. You do not have to build computationally expensive RNN models. And in other cases, sequence models work really well. So this is one of the interesting graphs that we saw. Like normally the practice is to take like top K number of features, and we found that this caps around like 20,000, beyond which for pretty much for all the data sets that we tried, the accuracy plateaued. No new information like helped with improving the accuracy. Haven't shown here, but in some cases, like if you take too many features, that this graph starts dropping because of overfitting. So about Keras, so as mentioned, I was an ML newbie when I joined the team. So Keras really helped my onboarding process. It made it really simple. That's how easy the APIs are. I'm sure like some of you who have tried the APIs would have felt the same. And so Keras API, it's high-level machine learning API, which sits over different ML frameworks like TensorFlow, CNTK, MXNet, and so on. And it supports training on CPU, GPU, and now TPU as well. The TensorFlow Keras module is called TF Keras, and TF Keras is optimized especially for TensorFlow, and it provides with all the TensorFlow features such as TensorFlow eager execution. It is integrated with the TensorFlow estimator high-level API for better serving. And so Keras has very few concepts for you to know and remember, which is what makes the API very simple. So basically, there is this concept of layers. If you have a model, if you want to build a model which is single input and single output, you have to linearly stack these layers, and that forms a sequential model. And there are a few other types of models. And once you've built the model with just a single line of code, which I'll show in a few seconds, you can train your model, test your model, predict, all with just a single line of code. And you also have the option to save and serialize with Keras. So this these are types of models that I talked about. So single input, single output is linear stack of layers, which is a sequential model. And if you have multi-input, multi-output, the type of model to use is a functional API. And so if you have a use case where you want to reuse a set of layers, typically use model subclassing. And so this is the simple MLP two-layer model that I actually used for classifying IMDb dataset, and this is how easy it is to write code for that in Keras. It's literally 5 lines, and so this is how you instantiate a sequential model, and you add different layers. Dense is basically a fully connected layer to the model. So I have added 2 dense layers along with dropout for regularization. And this particular model is for binary classification. So we have 1 unit in the last layer with activation function is sigmoid. So writing a separable CNN model is just as simple. So it's probably one additional line of code in order to add the embedding layer in the beginning. So instead of the dense layers that you saw, like we have a separable con 1D layer and with pooling layers. So for most of your use cases, using a simple sequential model will be sufficient, and it is just as easy to write a functional model as well. So here, so I talked about like fine-tuning your model. So to be able to do that, all you have to do is change the embedding layer. So you add these additional parameters like weights from pre-trained embeddings, and you set like Boolean value which indicates whether the layer is trainable or not. So when you want to fine tune, you initially set this layer to not be trainable, so that rest of your model, like it goes from initial random weights to better state, and then you set this layer to be trainable so that it is fine tuned with the rest of the layers. So that is it. Like, so I have links here to the guide, the code, and Keras as well. So please take a look and let me know if you have any questions. Thank you.